Question 6 can both be thought of as a vertical projectile motion problem as well as an energy problem. We have a paratrooper with a mass of 110 kilograms jumping from a height of 500 meters. This is enough information to give us the gravitational potential energy. He eventually hits the ground with a terminal velocity of 30 meters per second. This is enough information to give us his kinetic energy when he hits the ground. The next sentence then takes us into the second part of the problem, which is about the snowbank giving way, creating a crater of 1.5 meters deep. So this is 1.5 meters below the ground. It's quite helpful to have a diagram in this situation, because a diagram helps you keep track of all the relevant information as well as visualize what's going on. Here we have a paratrooper jumping from an initial height of 500 meters. He then falls until he hits the ground, which we'll call 0 meters. So the ground is the reference height of 0. And then he creates this crater here, where this area is indicated by still being snow. He creates a crater that is 1.5 meters deep, or 1.5 meters below the ground. Question 6.1 asks us to calculate the initial gravitational potential energy of the paratrooper relative to the ground. So this is further information that says we should treat the ground as the 0 reference point. Formula: gravitational potential energy is equal to mgh. Substituting values into that formula gives us a very easy 539,000 joules for 3 marks. In question 6.2, you are asked to calculate the paratrooper's kinetic energy just before he lands in the snow. Here we need to use that terminal velocity of 30 meters per second, the formula for kinetic energy, half mv squared. Substituting into that formula, and we get 49,500 joules. Also another easy 3 marks. At this point, it is quite useful to pause and think about the reasonableness of these answers. For example, why in 6.2 is the energy much less than the energy in 6.1? Energy is normally conserved, unless an external force is acting on the system. In this particular case, air resistance must have been acting on the system to cause the paratrooper to eventually hit a terminal velocity, the velocity at which is constant and speed no longer increases, in which case energy was being lost. Air resistance was a dissipative force, removing energy from the system, so it makes sense that the energy of the paratrooper has decreased. In 6.3, we are asked to calculate exactly this. We are asked to calculate the total work done by air resistance on the paratrooper while he falls. Now, the easiest thing is the work due to air resistance is the change in mechanical energy. Your final value for mechanical energy was 49,500 joules. That was in the form of kinetic energy. Your initial amount of mechanical energy was 539,000 joules. This was the gravitational potential energy when the paratrooper first jumped. This gives you a difference, there should be an equal sign here, of 489,500 joules, which is negative. The significance of this negative sign, again, work is a scalar quantity, so the negative sign does not tell you direction. Instead, that negative sign tells you that energy was removed from the system or energy was lost. An alternative route to answering this particular problem is to use the work energy theorem, where your net work is equal to your change in kinetic energy, and your net work is also equal to the sum of forces acting on your object. Therefore, your change in kinetic energy must be equal to the work due to friction plus the work due to gravity. Now, the change in kinetic energy we've calculated. Initially, you had 0 joules of kinetic energy because your paratrooper started without any kinetic energy, and the final value of kinetic energy was 49,500 joules. Work due to friction is what we're trying to solve, and the work due to gravity is negative 539,000 joules. Where this number comes from It's the exact same number that we have over here, which is the initial gravitational potential energy. You can get this number by using the formula for work done. Work due to gravity is equal to the force due to gravity multiplied by the vertical displacement multiplied by cos theta. Remember here, theta is the angle between the force and the displacement. The force is acting down. The displacement of this object, paratrooper, is also down. So cos theta is going to be 1 and theta would be 0. The magnitude of the gravitational force is mg. The distance through which this object has fallen is a height h, and here you can see that the work due to gravity is simply equal to mgh, which is the same formula we use for the gravitational potential energy. So that's where this number comes from, 539,000. There's a mistake here. This should be a positive sign, but that mistake isn't carried forward into the next line. So you'll see correctly that we get the work done due to friction is negative 489,500 joules, and energy is removed from the system. There are a couple of ways to tackle question 6.4, which asks you to calculate the average net force exerted on the paratrooper while he comes to rest in the snowbank. Firstly, we have two expressions for the net work done. Over here on the right, we have the net work done on an object is its change in kinetic energy. That we get from the work energy theorem. Over here on the left-hand side, we use the definition of work. Work is equal to a force multiplied by a displacement multiplied by cos theta, where theta is the angle between the force and the displacement. The net work done must be negative 49,500 joules. The reason for that is because it's the change in kinetic energy. The paratrooper started with 49,500 joules just before it hit the ground. By the time it got to the bottom of the crater, it had stopped, the paratrooper had stopped moving. So the work done, 49,500 joules, equal to the initial kinetic energy just before striking the ground, and negative because energy is removed from the system. Net force is what we're looking for. 1.5 meters was the distance through which the paratrooper traveled in creating that crater, and the force is acting up against the paratrooper. Yet the paratrooper continues to move down into the crater, therefore they are acting in different directions, so the angle is 180 degrees, so we'll be working with cos of 180 degrees, and that's going to give us this minus sign. They're going to cancel out. Doing the rest of the maths, you find that the net force is 33,000 newtons, and it's positive 33,000 newtons, so it is up. An alternative approach would actually have been to use an equation of motion. Vf squared is vi squared plus 2a delta y. Substituting your initial velocity of 30 meters per second, your acceleration we need to find. That's the purpose of using this equation of motion. The acceleration we find is 300 meters per second squared. So basically, that is the acceleration required to bring this paratrooper to rest within that distance of 1.5 meters. And then you can use Newton's second law. Your net force is equal to your mass times your acceleration. The mass of the paratrooper is 110 kilograms. The acceleration we've just found over here is 300 meters per second squared. And then finally, we arrive at the same answer. Your net force is 33,000 newtons up.